Welcome back. This is the last lecture, and we're going to complete our discussion of symmetry breaking in the context of gauge theories. That'll only take part of the lecture, and so for the remaining part of the lecture, I will give an overview of where to go next. But to begin with, I'm going to partially remind you of the stuff we covered in the previous lecture and clarify some points concerning the generation of mass and gauge theories via spontaneous symmetry breaking. So if you recall from the previous lecture, in the case where we have like a tuple of scalar fields, okay, so there's little d, that transform under some local gauge symmetry according to some group. This is what we did in the previous lecture, like so. Then we can, by adding a potential to the Lagrangian, so this is a local gauge of bosons. So if you take the Lagrangian and then you add onto it some potential term, which is minimized at some configuration, of this bosonic field, and if that minima isn't zero, then you can generate mass spontaneously. So that's what we learned in the previous lecture. And the example that we focused on is one where this minima has one component non-zero and the rest zero. You can always arrange for that to happen by exploiting the gauge invariance. Like so. So suppose we're in that scenario there, then the process or the procedure that we need to follow to understand the generation of mass, how the gauge bosons in this theory acquire a mass, is we look at the covariant derivative term. Now, in the previous lecture, the assumption was that this representation here is pure imaginary, that these matrices here had only imaginary components. And that's what led to the sign problems that we encountered at the end of the previous lecture. If you restrict to pure imaginary representations, then those sign problems don't occur. In general, if you don't have a pure imaginary representation of this local gauge group, then you should use a slightly different kinetic energy term in the Hamiltonian, in the Lagrangian, namely the mod squared of d mu phi. So that just means you have to add an extra complex conjugate, and that fixes up these minus signs that we encountered in the previous lecture. So that's the first stage of generating mass. And so this is some non-complicated expression. And when you expand this long complicated expression in terms of the phi equaling some phi classically plus some fluctuation field, d phi, I guess I won't use that notation. I'll just write phi. So we expand this this covariant derivative term in powers of this small fluctuation field around this.
Sorry, you had a bad notation.
Isn't that a bad notation? Oh, yeah, you're right. That is actually a bad notation. What did I use in the previous lecture? I used 1. You expand the covariant derivative term around this classical configuration here, then you get lots and lots of terms, of course. But you get, crucially, get one very interesting term, and that's this mass matrix term. We counted that in the previous lecture. We'll write it out here. So it's this term here which leads to the spontaneous generation of mass in these gauge theories. Now, in order for that to actually be a mass term in a Lagrangian, we need that this thing here, this is this mass matrix, which I believe I notated as little m AB squared. That mass matrix there has to be negative, has to be positive semi-definite, or it'll end up being negative semi-definite because of the metric here. So this is the last point that I need to clarify before we move on to the final model. So let's call this term star. So the first thing to notice is that because the metric has minus signs in it, it's almost a mass term. Write it out very slowly. So there's minus signs in there. So the 3 spatial degrees of freedom in this term here, if MAB squared is positive semi-definite, lead to a term which looks like a mass term in a Lagrangian. Remember, the mass terms of Lagrangians have a minus in front of them. And it's only this term here which doesn't look quite right. But it turns out we know how to eliminate this longitudinal term in the Lagrangian here. If the degrees of freedom of this theory are such that these gauge bosons are always transverse to the direction of momentum, then this term plays no role. So with photons, the excitations of the gauge field U1, we know that the actual degrees of freedom are transverse to the momentum of the photon. There's no longitudinal degree of freedom for a photon. It's always eliminated. So there's a fewer degrees of freedom. And as long as that's the case for these more general gauge theories, then we have a legitimate mass term here. And so the way So the way to check if the gauge bosons are transverse in the quantum theory is to study this vacuum polarization diagram. So that's this process here. Which I sketched how to do in the abelian Higgs model. I'm not going to go through the full details here, but the diagram, the lowest order, which does the job for us, is this one here. That diagram there cancels off the longitudinal contribution that would otherwise come from this term here. At second order, and so we know that there's dot 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 plus plus. So we learned that this vacuum polarization process, when you work everything out, is like this, which is transverse. So has exactly the right form. And in the example that I considered at the end of the previous lecture, SU2 in the fundamental representation, if you use this definition of the covariant derivative here and work out this mass matrix here, then you end up with as we hope that the mass matrix is proportional to the identity, which gives all three bosons in that theory a mass. And they are transverse according to this diagram here. So that's the brief summary of where we've come so far. Now, I'll just give a short sketch of how this is applied to theories where there are massive bosons and massless bosons. Massive and massless gauge bosons. And how does that work within this general framework here? How is it possible to give some bosons a mass and some not a mass by this mechanism? Because nature has chosen, as far as we know, to give photons no mass. I mean, the current bounds in the photon mass is something like, I don't have the numbers in my mind, but there's something like 10 to the minus 30, 40 or something or so. I mean, we have not proven that the photon is massless, but it is extraordinarily light, according to the best bounds. But the gauge bosons, W and Z, they all have a mass. So if this all comes from some gauge theory, we've got to wonder how do we arrange things so that some of the gauge bosons have a mass and some don't. So that's the thing we've got to finally sort out. And then there's a bunch of other wrinkles that you need to deal with in order to build a nice quantum field theory of all the known interactions. We're not going to be able to cover all those details in this course. We've reached the last lecture, of course. But I will say a couple of words about it. So at a very high level, we're going to sketch this GWS theory of weak interactions, which describes SU2 gauge bosons and the electromagnetic field and how they can be combined together in one theory. Here, the local gauge group is now SU2 cross U1. In this theory, this is part of the standard model for elementary interactions. And how does this act on our boson field? Well, we have a doublet. And the way it acts on our boson field is according to this representation here. So let me just clarify what this is. So phi is a doublet, a triplet, a doublet. And these are the Pelby matrices. And this is the scalar. So this is how the SU2 part acts, and this is how the U1 part acts. So tau A is sigma A12, Pelby operators. So this is a representation of this group here, SU2U1, on a pair of boson, scalar boson fields, phi 1 and phi 2. So that's the first ingredient of this GWS theory. We need to find a way to represent this gauge group on the boson part of the Lagrangian. There will also be a fermion part, which I'll mention at the end. And that's how we take it to act. So it gives this boson field a charge of a half, if you like, under U1. So you can check that that's a nice action of this D group, and all is well so far. So next we add a potential to L so that phi wants to oscillate around the classical minima of this potential. And that classical minima will be exactly the one that we had in the previous discussion up here. We put a group 2 in there for convenience. And then we're going to expand the covariant derivative around this. Well, to do that, I would just first write out the covariant derivative. What does it look like for this particular funny gauge group here? Well, if you went through all the steps of deriving a gauge theory that we outlined in the previous lectures, and then just generalized it at every step to this group and the way this group acts. We introduced parallel transporters, of course, and then connection fields. You'd have a connection field, you have 3 connection fields for SU2 and 1 for this part here. And so, okay, once you do all that, this is sort of a reasonably good exercise. I'll leave that as an exercise there. Then you end up writing something that looks like this for the covariant derivative. That is how the covariant derivative looks for this gauge group here in the fundamental representation. And we've got now 2 connections, so to speak, or one sort of big connection. So you can organize this these connectional gauge fields into like one big list of gauge connection fields if you want. Or you can think of them just as 2 different connections of gauge fields, one for the SU2 part of the group and one for the U1 part of the group. So, and then you build a Lagrangian invariant. Has such terms as this, it has such terms as this, plus blah 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 blah, plus fermion terms which we'll talk about presently, and then the full GWS Lagrangian has this potential added in here which is also gauging. So let's now look at the mass generation via this SSB or spontaneous symmetry breaking that occurs when this potential has this particular minima there. So you go through all the steps and you require expand around phi classical, and then you require a term from the covariant derivative term, this kinetic energy term. What does it look like? Well, let's have a look. And it's an exercise, but now it's very, very routine exercise because it looks exactly like the things you've been doing all along. So after all the dust settles, after doing the expansion around this classical minima, of this covariant derivative kinetic energy term here, we end up with a term that looks like this. So these three original gauge bosons get combined with this U1 gauge boson field here. And if you sort of squint at this long enough, this looks exactly like a mass term with three particular gauge bosons. But one of them is a bit different from the others, right? There's this guy. So somehow the A1 mu degree of freedom behaves as though it has a mass, the A mu 2 degree of freedom behaves as though it has a mass, and this particular linear combination of the A3 mu degree of freedom and the B mu degree of freedom has a mass. And there's a fourth degree of freedom because there are four gauge bosons here. There's three coming from SU2 and one from the U1. There's a fourth degree of freedom which doesn't acquire a mass, it's massless. So it's convenient to give these fields different names, just to relabel them, by introducing new linear combinations of these guys. And these are the ones that we attach to the actual gauge bosons of the Gauge theory. So these are just functions, A1, A2, A3, B, mu. And we can form linear combinations of these functions. We can give them different names to attach them to particle fields that we actually have received in experiments. Namely, these two W bosons and this Z boson here. We're just going to attach this particular linear combination to the W plus boson, and here with the plus to the W minus boson, and we attach to the Z naught boson this linear combination here. And there's a fourth linear combination which is zero, which has a zero mass, and that we attach to the photon. And that fourth degree of freedom here, A mu, without the superscripts, that's what we attach to the photon. And it has zero mass according to this prescription here because it's annihilated by the generator of the U1 transformation. This is the mechanism of mass generation for the GWS theory for these gauge bosons. We've only talked about the gauge bosons and this additional field phi here. What we haven't yet talked about is how these fields couple to fermions in this theory. And there are some additional wrinkles, namely that the gauge bosons couple in different ways to the left chirality solutions of the Dirac field than they do to the right. This is a very the left-handed and right-handed fields in the Dirac equation get coupled in a different way to these boson fields, which is sort of, at first sight, impossible. But I'll just say a couple of words on why, on how that can happen. So if you remember that when you add some fermions, that when you consider the kinetic energy term for fermions, then when the fermions are massless, when the fermions have no mass, then this term here decouples into a term that only talks to the left-handed fields and a term that only talks to the right-handed fields. So this is just the way the gamma matrices work. This was back in the first course on quantum field theory. This term here decouples into these terms here. So the mass term is what couples left-handed and right-handed parts of the Dirac spinner. And if you didn't have a mass, then they wouldn't talk to each other. Now, in a gauge theory, you change this d to the covariant derivative, but otherwise, same arguments apply. There's this decoupling between the left and right-handed fields. Now, we observe that these gauge bosons couple differently to the left-handed fields and then to the right-handed fields. It's just what nature has chosen to do. We're stuck with that. And the question is, how on earth could you realize that? How could you realize this difference in coupling between the left-handed and right-handed fields in a local gauge theory described by some of Young-Jin? Well, there is one degree of freedom that we haven't really exploited so far, and that is that we can choose different representations of the same gauge group, and they will lead to different theories. Every time you choose a different representation of the group SU2, you'll get a different theory. It'll couple in a different way. It'll have different connection fields. It'll couple in a different way to the boson degrees of freedom. Similarly, it'll couple in a different way to the fermion fields. And so in here, this covariant derivative term includes the gauge bosons, which in turn are described by the representation of the gauge group that you were using. And so you can write down a locally gauge invariant theory which couples differently to the left and right-handed field by choosing different representations of the gauge group in the left-handed and the right-handed part of this Lagrangian net. Super weird, but that's what nature has chosen to do. So we're kind of stuck. I think that's pretty much all I'm going to say on this topic. I'll just say that, I'll write down that comment here. So if you want a theory to couple differently to the left and right-handed gauge bosons, fermion fields, then you need to use different representations of SU2 in this covariant term, derivative term, and in this covariant derivative term. That's just the way things are. that's the end of the content for this course in terms of the material we need to cover. I've given you a tourist guide, that's the only way to describe what I've done, a tourist guide of advanced quantum field theory and how it applies to the theory of elementary interactions given by the Standard Model. Now, of course I haven't gone into the details, and there are very, very many details that I haven't covered. Just doing the quantum theory correctly for mass generation is a very intricate and difficult business. Dealing with these different representations here is a difficult and intricate business. Checking that symmetries that you're at the classical level are maintained at the quantum level is a difficult and intricate business. And there's a lot of engineering details in how you pull off these calculations. So quantizing these theories, summing the diagrams, checking that things, how to run the coupling constants so that you get finite answers at the end. Incredible numbers of details are required to actually to build this theory, the Standard Model of elementary interactions. And I haven't done these details. You have done some of the details in the exercises, but I have not shown you line for line how this full model is generated and how it's worked with in the real world. We also haven't covered QCD, the theory of gluons and quarks either, although that's less complicated morally than the weak interactions in some ways. So there's much that hasn't been covered. But what I've done in this course, the objective was to let you see like some tourist snapshots of what the various stages of this process look like. So that if you want to, in your own time, study the Standard Model in more depth and go through these details, you will have seen all the processes, you just have to put them into action. Now, in terms of learning more quantum field theory, this is where it more or less stops. So I've given you little snapshots of the chapters of modern quantum field theory textbooks, and we've reached basically the end of the more advanced textbooks on quantum field theory. So there's not much more material that you can find at the textbook level, and there doesn't need to be, right? If you want to go out and do practical calculations at the LHC, then with enough self-study, you'll be able to do it with what I've taught you in these courses. But it's definitely interesting to ask, well, where to now? Where do you go after advanced quantum field theory? If you don't want to do practical particle theory calculations, what's the open problems in this field? Where do you look if you want to actually go beyond textbook material to research material? So in the final sort of half of this lecture, what I'm going to do is give a very superficial overview of research directions that now begin roughly at this stage of your understanding. Where does one go after learning advanced quantum field theory? So one place to go is to just is to do practical calculations of things in experiments. So that's really a very important business. You want to check that this theory of the elementary interactions, the Standard Model, matches the experiments, well then you need to go and do lots of calculations, make predictions for what you would observe in particle accelerators. This is one at this moment, very active direction. And then of course, there are others which are much more speculative. So what we'll do is I'll divide this discussion now into two parts. The first part is if you want to investigate physics more, but not worry so much about mathematics. And the second part, which I'll also spend quite a bit of time on, is describing the mathematical status of all these results and where to go to next there. So in the physics literature, an extraordinary amount of activity has centered around upgrading the group of symmetries of your theory. So because of this Coleman-Mandela theorem, which I won't go into, there's not very many places to go if you want to consider more general quantum field theories with more general symmetries. But there is one particular direction you can go in, and that is the direction of supersymmetry, enhancing your Poincare group to have more symmetries, which allow you to transform between bosons and fermions. So this is the topic of supersymmetry. And a great deal of energy has been expended studying supersymmetry because it offers an explanation of so many tantalizing mysteries that the standard model leaves open. So as yet, the experimental status of supersymmetry is not clear. I think is a fair way to say it. And there's another direction that people in physics have adopted, which is taking this particle theory-like way of thinking about elementary particles and applying it to our other theory, namely quantum gravity. Namely gravity. So there's a great deal of work, to put it mildly, in studying what a quantum theory of gravity looks like if you use quantum field theory tools. So it's possible to take Einstein's theory of relativity, general relativity, and think about what a quantum theory might look like without using field theory tools. But that's a harder job than the task of interpreting the general relativity as a classical field theory and then trying to quantize it, trying to come up with a quantum field theory. And so a lot of people have focused on using field theory tools because they've been just so useful and so effective to understand quantum gravity. So in that direction, probably the most natural marriage of field theory and gravity is superstring theory. So that's, I need not say very much more about that. There's plenty of material on the internet if you want to learn more about superstring theory. But that's in this tradition of taking the things that we've learned from field theory and applying them to gravity. Except in string theory, it sort of turned out a bit different historically. And gravity emerges not in the most direct way imaginable. So that's really an extraordinarily active part of research, and it's very, very much ongoing today. The marriage of quantum gravity and field theory via this assumption that the degrees of freedom of the theory are actually strings rather than point-blank particles. So it's very popular. It goes a lot of places. There's another approach, which I think is fair to say doesn't quite starts in a completely different direction. That's loop quantum gravity. I won't say very much about that. I'm not qualified to speak about either of these topics, but less so about loop quantum gravity. There are several approaches to quantum gravity by field theory tools that don't go directly to string theory. And one way is by linearized quantum gravity. So you take some field, the metric, as your fundamental degrees of freedom, and you study perturbations of this metric and treat these as quantum fields, these perturbations here. And there's a lot you can do. And then you study the Einstein-Hilbert action and attempt to find a quantum version of that. And you write down all the interactions to, say, second order in this G, and then you study the corresponding quantum theory where you put a hat on everything here. So it's, properly speaking, linear quantum gravity because we didn't write down strings or anything, we just directly wrote down a field theory for linearized quantum gravity. And there, if you combine this with the standard model, we have the best effective theory that we know for describing all the interactions that we've observed today. So, So it's worth pointing out that quantum gravity is not renormalizable. So that means if you want to make finite predictions using a finite number of coupling constants, then you can't do this. You need to keep adding in coupling constants to make sure that all your predictions at low energy remain finite as you lift the cutoff. So what people do, what you can do very, very effectively, extremely effectively, it's worth emphasizing how extremely well this works. If you take linearized quantum gravity, you put in some cutoff, and just ensure that predictions of this quantum gravity theory match normal gravity up to some experimental threshold, then you get a perfectly workable effective theory of gravity. You can even work out corrections to graviton scatterings. You can work with this full theory, but there is this cutoff in there. You can't get rid of that. If you want to move the cutoff, you have to add in interactions. But if you're willing to just leave that cutoff at some number, 10 to the 34, for example, leave it there at that finite number, and match all the low energy experiments in the way that I showed you with renormalizable, with adding counter terms, then you can generate a whole sequence of predictions from this theory. It's often downplayed the success of linear quantum gravity, but it's extremely powerful. It really can. We know exactly all the correction terms that will come from any theory of quantum gravity simply by understanding linear quantum gravity with a finite cutoff. If you couple linear quantum gravity and the standard model, then you get the best effective theory that we know for describing all the experiments we've seen today. So this is an extraordinarily good effective theory, but we believe it's wrong. We believe this effective theory is not fundamental. So that's worth emphasizing that although this effective theory can match just about every experiment we've ever performed, we have fundamental reasons to believe it's not fundamental. And there's the one reason we believe that most strongly is because of these things. So black holes are, well, we believe we've experimentally observed them, at least we've inferred their existence, we haven't directly observed a black hole. One has not passed by us, close by it enough that we can look at it, but they're the best description of many astrophysical phenomena that we've seen. And because we know that there's black holes out there, there's a tension between this effective theory and these objects which we believe are out there. And the tension is linear quantum gravity as an effective theory isn't capable of describing black holes. Because black holes really require that you understand what's going on at the cutoff length, right up at lambda. But that's precisely the region we're forbidden from looking at when you do an effective theory. So it's like using Navier-Stokes equation, this effective theory of water, to infer things about quarks and gluons. So Navier-Stokes equation is the best effective theory for fluid mechanics that we know. It works extremely well. It can model everything from supersonic aircraft down to the flow of viscous fluids. It's a great effective theory. This is the analogy to have here with linear quantum gravity. It works well in the low energy regime, but the minute you go to ask Navier-Stokes about the composition of protons, then it doesn't have much to tell you about that. And it's the same here with linear quantum gravity. Linear quantum gravity tells us a lot about low energy gravitational processes, about scattering of gravitons and so on. But the minute you ask it about high energy processes near the cutoff, like what black holes require you to do, then it throws up its hands and can't give you an answer. That's just like Navier-Stokes does. That's the situation we find ourselves in at the current time. We have this fantastic effective theory, linear quantum gravity, and the standard model. holes in any obvious way. And we do believe there are black holes out there, so we know that we need something more. There's a whole host of cosmological issues that this effective theory here doesn't do a very good job at either. Dark energy, dark matter, the expanding universe. Lots and lots of situations where this effective model doesn't really offer much in the way of an explanation. It can just model what we see very well. And so, of course, what people are really fascinated with is the idea that they could, from some basic principles, come up with a arguably simpler theory that has as its low energy limit linear quantum gravity plus the standard model, and which gives a simple explanation for the physics of these things. And that's what superstring theory is felt to offer. So superstring theory is arguably simpler in the sense that it has not very many free parameters. It has roughly one, which can take a horribly large number of values, but it has one free parameter, effectively. And that means that the amount of complexity input to this theory is very small, but its low energy effective theory is thought to be captured with linear quantum gravity plus the standard model. So superstring theory offers a simple explanation for complex things, such as black holes. That's why people are excited by it, because it offers this conceptually simpler way to explain a lot of experimental data. Now, whether or not it's correct is a subject to debate. Whether or not it's falsifiable is also an intricate question that I won't get into here. Now, there's one further aspect that emerged from superstring theory, and that is a very surprising idea that maybe you can explain gravity not via strings but by quantum field theory itself. So this goes under the rubric of this so-called ADS-CFT correspondence, which roughly says so ADS-CFT correspondence says this in this box here. The ADS-CFT correspondence of Maldacena, most sort of beautifully captured by Maldacena, but also dating back to ideas of Susskind, approved, and Brown and Moe, tells us that a strongly interacting conformal quantum field theory is dual to a quantum gravity theory of anti-de Sitter space in the semi-classical limit. So you don't need to know what half of this terminology is to appreciate what this is telling us. So the take-home message that I think is prevalent today is that there's one thing we don't know what it is on this correspondence, and there's one thing that we do know what it is. So it turns out that we're quite comfortable with those words there. Right? So we have these things called conformal quantum field theories, about which I'll say something presently, and you can imagine that there is such a thing as a strongly interacting conformal quantum field theory. And such a conformal quantum field theory is meant to be dual to some object, namely a quantum gravity theory of this anti-de Sitter space. And about this thing we know less, right? And so what the one interpretation of this ADS CFT correspondence is this is a definition of what a quantum gravity theory is. According to a certain dictionary of things, to every observable in this I didn't say the word boundary here. So to every strongly interacting quantum field theory that we think of as living on the boundary of an ADS space-time, about which you need not know either to understand to appreciate what's being said with this correspondence, we say that such a strongly interacting quantum field theory is dual to this quantum gravity theory. We see this now as one interpretation is this is the definition of what a quantum gravity theory is. A quantum gravity theory of anti-de Sitter space-time is now understood. It's now understood how to build such a thing just from a quantum field theory. So the answer to the question, what is quantum gravity, according to this correspondence, is it's just quantum field theory. So in the past decade, there's been an extraordinary amount of work done on this, exploring this correspondence here, this idea. And it's been confirmed, and in some senses proven, certainly the level of physical rigor, for this particular setting of anti-de Sitter space. You need not know what anti-de Sitter space is, except that it's a solution of Einstein's equations. And so this really is probably one of the most exciting ideas in the direction of quantum field theory and quantum gravity together, because you can spend all your energy, say, learning about quantum field theories, and then for free, you gain intuition about quantum gravity theories according to a very precise dictionary that's been developed to understand this correspondence here. So that's really still an extremely active field of research, and it continues to this day without break. But of course, there's one criticism that people make, namely that anti-de Sitter space is not the space-time we find ourselves in. So the open direction here is de Sitter space, which is the space-time that we find ourselves in. There's only very little work on this topic at the moment. There is a kind of correspondence between that mirrors this analogy here for de Sitter. But I think it's fair to say that it's not fully explored yet. But we're gaining confidence in this part of the correspondence. We now believe this really is correct understanding between the duality of these two theories, and therefore, if you like, a definition of what a quantum gravity theory looks like. And we can use that confidence to now move on to this more relevant setting here. So this is absolutely current active research here using quantum field theory tools, often ones that you've already seen in this course. And I think that's where I'll end my discussion of the physics part of where to go. If you were going to look at research now in high energy physics, then you would probably gravitate towards, pun intended, ADS CFT correspondence, superstring theory, or perhaps loop quantum gravity, which uses a different set of tools to these research areas here, and addresses slightly different questions.
More question.
Yep.
What's written down after de Sitter?
This is the author, Strominger, who has studied the question of duality for de Sitter space. Well, that's the physics side. Of what to do next. Oh, before I finish the physics side, I might mention that quantum information theory has very recently been shown to be extremely helpful in understanding this duality here. So, because in the past decade we've learned very much more about the kinematics of quantum mechanics, in particular quantum entanglement, how does quantum entanglement behave what role does it play in understanding quantum mechanical systems, we've developed many new tools, and these tools have turned out to be very helpful in understanding many mysteries in this ADS-CFT correspondence. So quantum information theory is very helpful when you want to talk about strongly interacting conformal quantum field theory. And the better you understand this side, then according to this duality here, therefore the better you will understand this ADS quantum gravity side there. So there's been some very strange mysteries in this duality that have been resolved by using ideas from quantum information theory. There's absolutely cutting edge research. People are actively writing papers on this right now as we speak. So that's the physics side. That's where I see like the activity happening on the physics side. It's in doing calculations, phenomenological calculations for experiments, testing out modifications of the standard model. Do they do a better job of matching what we see? It's also, research is focused on finding more economical descriptions with this effective low energy physics that can deal with black holes, and very closely related to that is this idea of defining quantum gravities via this ADS CFT correspondence there. And none of those, I think it's fair to say, none of these areas of research really work at the level of mathematical rigor. So that's something that I know many of you are dissatisfied with in this course. It's just the nature of what we're doing right now, that the mathematical tools haven't really yet been developed to properly talk about quantum field theory at a mathematical level of rigor. So what I'll do in the last part of this course is give you an outline of where the mathematics actually is right now. What do we know is true? What are the mathematical tools that have been developed? And there are really a lot. There's a lot of energy has been spent studying quantum field theory at a mathematical level of rigor. And there are quite a substantial number of results now that have been accumulated over 50, 60 years of research. So there's multiple approaches to coming up with rigorous formulations of QST. Multiple. Mathematicians have not been lazy. They have been actively working very hard trying to understand physicists and trying to capture a mathematical formalism that would settle or at least put on a rigorous footing many of the calculations physicists successfully carry out. So I'm going to list basically an exhaustive list of all the approaches that people have adopted. To build a mathematically precise formulation of quantum field theory. Here's the laundry list of mathematical approaches that have been taken to understanding quantum field theory. The first is axiomatic quantum field theory. Axiomatic quantum field theory, what you want to do is isolate a bunch of axioms that you add to quantum mechanics that any quantum field theory ought to obey. Right? So this is historically one of the first approaches people took to making a mathematically rigorous version of quantum field theory. Mathematicians looked very hard at what the physicists were saying and what they were doing, and isolated a bunch of axioms. That captured the essence of what a quantum field theory ought to be. So according to the axiomatic characterization of quantum field theory ought to be a quantum mechanical theory. So any quantum field theory better behave the laws of quantum mechanics, according to the laws of quantum mechanics. And then they added some axioms to that. So what I'm going to, before I give a sketch of all these mathematical approaches here, you can, if you want to learn more about any of these particular approaches, by Googling them, these keywords, you will find decent introductory articles to each of these things. I'm going to spend, before I briefly summarize what's going on in all these approaches, I'll explain why it's hard. That's probably more important. Let's at least spend some thought before we look at these formulations, understanding why it's hard in the first place to make it rigorous. You know, in some sense, it shouldn't be so hard. Physicists every day do calculations with what they call quantum field theory and come up with finite answers. And I've stressed very often that quantum field theory as an effective theory is a perfectly well-behaved theory. So what on earth is so hard about this? Well, I think, one core reason is that perturbation theory is so good. This sounds odd as an answer, but it's actually. Perturbation theory works so well, and it's the only tool we have. Which is not fair. I'll deliberately cross that out. But it's the standard tool we have. Maybe that's a nicer way to say it. As you'll see, very presently, we have multiple tools for dealing with quantum field theory. But the first reason why it's hard to make rigorous is that perturbation theory works so well, it's the standard tool, but we know that it's wrong. And we know why. And I'll give just the simplest zero-dimensional example, which pretty much captures everything that's wrong about perturbation theory and also everything that's right about it. So if you look at the example of one that you covered, I think, in the previous course, namely an action for a zero-dimensional particle, which is just if you like this. So all our path integrals for quantum field theory have this kind of general structure. They look like something Gaussian, right? I've stressed this over and over again. When you do perturbation theory, you start from a Gaussian theory. And what's the simplest Gaussian? Well, it's a Gaussian. It's the world's simplest theory. And some perturbation like this. Now, if you assume G is smaller than you do perturbation theory to understand this integral, then you get some series. Already here we see all the problems that we have in quantum field theory at this very trivial level of a single 0 plus 1 dimensional system that's basically just one integral. If you do that, you get a massive explosion of terms. You get lots and lots of terms in powers of G, and the radius of convergence is 0. Oops. Okay, so that's really, I mean, this should not be surprising. This is just, it's just the way it is. But look back at this integral here. So the problem with the radius of convergence of 0 is to do with the fact that there's lots of possible terms in this perturbation series as you go in higher in powers of G. But if you look at this integral, like forget perturbation theory, just look right back at this integral here, then this shouldn't just be convergent, it should be extremely convergent. Like if G is 0, well, we have a nice convergent Gaussian, all is good, right? But if G is not 0, well, that thing is positive for all x, and there's a minus sign here. So, hello, you know, this should be more convergent when you add G. And that's precisely true. There is no, that's exactly what's going on. The interaction term here, if you like, only improves the convergence of this integral, but perturbation theory can't make use of this information. So the whole theory looks well behaved, indeed it is, but perturbation theory does not give you that impression. Now in the path integrals we consider in quantum field theory, the more complicated ones, if you do a Wick rotation, all have this structure. So we actually think that they should be beautifully convergent. It's just we can't calculate them. So when you have a situation where you have something where you think is well behaved, and your only tool is not well behaved, then that makes your life very difficult. So that's one of the reasons why quantum field theory is hard to make rigorous, because the standard tool that physicists use isn't the one that will prove that the thing works. And now what I'll do is explain, give a brief summary of all these formulations here, and how they deal with this apparent dichotomy here between perturbation theory and the theories that ought to be well behaved. There's one other thing, another reason why quantum field theory is hard to make rigorous. So there's lots of evidence that physicists have accumulated over the years that tells us for 6 space-time dimensions, in fact more than 6 space-time dimensions, the only non-trivial, all QFTs are trivial. Gaussian. So physicists believe, on the basis of renormalization group arguments, that if you go above 6 space-time dimensions, the only quantum field theories that will exist even at a physical level are ones that are trivial. So the only non-trivial ones can occur below 6 space-time dimensions. And that's also something that would require you to have a very good understanding of how interactions work with your theories. So that's also another reason why quantum field theory is hard to make rigorous. the tour of the mathematical formulations of QFT.
One question.
Yep.
And if every quantum field theory above 6 dimensions is trivial, but the string theory is in more than 6 dimensions, and you said superstring theory is a very good theory.
Yeah, okay, so so the question is, if all theories are trivial above 6 based on dimensions, but superstring theory lives in a higher number of dimensions, what's going on with that? Well, the answer is that superstring theory is not a field theory. It's not a theory of fields, it's a theory of strings. So a theory of fields is a theory of point particles, and a theory of strings is a different beast altogether. So it evades this simple observation. In the beginning, there were attempts to work out the axioms that any quantum field theory should obey. And 3 sets of axioms were developed. And here's the axioms. So historically, the first were a set of axioms called the Whiteman axioms, which describe quantum fields in terms of unbounded operators in some Hilbert space. Or distribution valued objects acting on a Hilbert space, on some Hilbert space. Then there was the axioms of Hagen and Casley, which translate that to something involving C-star algebras. And then we have the axioms of Osterwalder and Schrader, which are focused on understanding how to get a quantum field from a statistical mechanical system. My interpretation is statistical mechanical system. But another way of saying that is like, if you have a weak rotator theory, where does that give rise to a quantum field theory? So these are the 3 axiom systems that have been adopted in the early years to try and make sense of quantum field theory. 3 of them, Whiteman axioms, Hagen-Casley, and Osterwalder-Schrader. And the focus of all these was on reconstruction theorems. Which tell us that if we have enough correlation functions, we can reconstruct the Hilbert space and the unitary representation of the Poincare group. Okay, that's the focus of the axiomatic approach. There are a bunch of axioms on the endpoint correlation functions of your theory in 3 different settings. And if your endpoint correlation functions obey a certain number of conditions, then you can reconstruct a full Hilbert space for your theory, and you also get how the Poincare groups acts as a unitary representation. And so that's a largely successful program in mathematics, but it's sort of stopped when it comes to gauge theory. So there it is. This is where the current research is more or less at. if you want to prove a reconstruction theorem for local gauge theories, there is work in this direction, but it's still very much open research topics. Then we come to the next approach to making sense of quantum field theory. This is called constructive quantum field theory. In constructive quantum field theory, you look at this observation here and you try to make use of it. So you take the Wick-rotated or Euclidean half integral for your favorite quantum field theory. You immediately observe that things should be very well behaved when x is large. When x is very large, this thing here only makes the integral more convergent. And then you trade off perturbation series at low energy with estimates for large values of x that suppress the badly behaving part of the perturbation series. You trade all this stuff off together to come with a finite answer. So constructive quantum field theory leads to a systematic way to deal with these kind of integrals called the cluster expansion. And then by studying intricate trade-offs in this expansion, you can end up with finite results. And this has been very successful. In 1 + 1 dimensions, with some work in 2 + 1D. But the proofs are, well, to put it mildly, a little bit intricate. Some of them reach the limits of human communication. Especially when you deal with local gauge theories. There's a series, several authors have attempted to do this program on local gauge theories and have written a series of 13, 15 papers, and it's getting to the point where you can scarcely communicate the results because they're so intricate and lengthy. Makes it also very, very difficult to verify. So this is not wrong. I think we have every reason to believe that this program will succeed, but it's getting very, very difficult to work in this topic. Algebraic quantum field theory here. In algebraic quantum field theory, you take these axiom systems very seriously, and then you try and abstract what are the observables. You do it the other way around. You don't look at the states, which are the endpoint correlation functions. You look at what structure the observables have to have. And you ask yourself the question, what does locality mean in quantum field theory? You create a set of mathematical structures that quantify what it means local in a quantum field theory, and that gives you an observable algebra, which happens to be a C-star algebra. And you can prove lots and lots of results about these theories because you have a nice C-star algebra at the end. But here, a core challenge is again centering around local gauge theories. How do we find states now for these observable algebra? States, which are otherwise known as endpoint correlation functions. How do you find states for these algebras that correspond to theories that we have in experiments such as the standard model? It turns out there's very, very many states for AQFT, uncountably many. The trick, or the challenge, is to find the right ones, the ones that match our experiments. Functional integration and expansions, which will stick together with probabilistic approaches. another axiom system where you take the functional integral as defining a probability measure. So you may have heard scary things said about the non-existence of measures in infinite dimensional spaces and so on. All of this is really a red herring. If you go back to the path integral and you look at it, you don't really want there to be an integration theory for infinite dimensional spaces to make sense of the path integral. All you want is that for one particular probability measure you can make sense of it. And that one particular probability measure is one that is the action of, say, the standard model. So if you try and make sense of the standard model as a probabilistic theory, you want the measure that you get out there to obey axioms, and these would be classified as Nelson's axioms. And they make sense of path integrals as probability measures. It's worth pointing out that Nelson's axioms are stronger than these Osterwalder-Schrader axioms. So there's some theories that would be allowed by Osterwalder-Schrader, but not by Nelson. And this is pretty much a good example here. So whether or not that's a good thing or not, I think very much depends on what you want. And then I'll just say aloud in words, rather than writing down any bullet points. Vertex operator algebras is really very much stuck at the level of 1 + 1 dimensions, but it's very, very successful in describing conformal field theories in 1 + 1 dimensions. And TQFT, which stands for topological quantum field theory, is a class of quantum field theories that are exactly solvable and strongly interacting, and they have a certain structure built on a mathematical apparatus known as n-category theory. So there's some far-out mysteries there. This is also a very promising direction to go if you want to understand what exactly solvable quantum field theories look like, what sort of data do they give you, and what structure they have. I won't say much about chiral and factorization algebras, except maybe to highlight the work of Costello, who's very recently achieved great success in studying quantum field theory, perturbation expansions. And I'm going to end all of this, and in fact the course, by saying that there's one mathematical direction that hasn't been explored as far as I can see in as much, well, there hasn't been as much activity as I would have expected. Namely, making sense of effective quantum field theory. And the origins of many of these approaches come pre-Wilson. So Kenneth Wilson came along and changed the way we think about quantum field theory in the late 60s and 70s. And these mathematical approaches can really trace their origins back to the way people thought pre-Wilson about quantum fields. And post-Wilson, we know that quantum fields are really effective theories of more fundamental things. And that's the reason why we get finite answers out of the machinery of quantum field theory, because we're always working with finite regularized theories. But actually, very little work has been spent on making this idea of effective quantum field theory rigorous. So I think that is kind of my personal favorite open direction left in the mathematical way, the mathematical side of things. It should be possible, I mean, effective quantum field theory always gives us finite answers. It should be possible to build a mathematically rigorous theory of effective quantum field theories. There's sort of surprisingly little work in this direction. I suppose it's tremendously less sexy than building a real quantum field theory with which has no cutoff in it. But this is really the way physicists work with quantum field theories, so it seems worthwhile to study this direction a bit more, just to make sense of what physicists are actually doing every day. So I think I will leave you at the end of this course with that question: what is the mathematical theory of effective quantum field theory look at? And thank you very much for your participation.